So, we are continuing with our discussion on graph representation learning. Particularly in the last lecture we have started discussing matrix factorization based approaches for graph learning, and we have seen GRAREP, which is one of such matrix factorization based approaches. And today we will discuss another algorithm which is called HOPE, higher order proximity preserving embedding. Okay. So, what is the intuition behind this algorithm? So, if you look at the network, right, in general most of the networks follow some sort of transitivity relations, right. I mean, if U is connected to V and V is connected to W, there is high possibility that U and W would also be connected, right. So, if you look at the algorithms which are proposed before HOPE, right. So, all these algorithms were mostly designed for undirected network, which basically is I mean, those kind of algorithms are okay when we have an undirected graph, right. And naturally this kind of symmetric transitivity, right, preserves this kind of symmetric transitivity is preserved in those I mean this kind of symmetric transitivity has been preserved by the algorithms. But if you think of a directed graph, right, say for example here U is connected to W, W is connected to V, there is a directed edge, there is a directed edge from U to W and another directed edge from W to V, right. Then if you imagine, right, it is highly likely that there might be a relation from U to V, right, because of this nature there might be a connection from U to V, but not V to U. So, in a directed graph, right, transitivity property is asymmetric, okay, and this is the whole story behind this algorithm, right. Transitivity relation between nodes in an undirected graph is okay, but transitivity is asymmetric in a directed graph if there is an edge from node U to W, as I mentioned here, and W to V, then the probability of an edge from U to V will increase, but not the other way around, okay. So, HOPE algorithm, this aims to generate lower order representations of nodes that can preserve the asymmetric transitivity in directed graphs, okay. So, this is the overall idea, and this was proposed in 2016 in KDT, okay. So, let me demonstrate it in using a figure, okay. These figures may not be very visible, but I will try to explain what this figure indicates, okay. So, you see here from V1 there is an edge, there is a directed edge, right, to V2 with certain weight 0.3. This weight is essentially some sort of proximity, okay. This proximity can be a card's proximity or a proximity which is already given, say a weight, right. There is another directed link from V2 to V4 with 0.3, right. Let us look at only this part. There is a link from V1 to V3 with 0.3, V3 to V4 with 0.3. So, you see from V1 to V4 there are two paths, there are two directed paths, one through V3 and another through V2, okay. So, it is natural that there might be a path, there might be an edge from V1 to V4, which is highly likely, but from V4 to V1 there is an edge, this is less likely, okay. So, you may see an edge from V1 to V4 with say some proximity 0.18, these are dummy proximities, okay, but from V4 to V1 there should not be any edge, okay. So, if this is the graph, if you look at the embedding space, right, in the embedding space what should happen? In the embedding space, of course V3 and V2 they would be closer to V1, right. V4 would also be closer to V1, but in a different aspect. Okay, I will discuss the aspect here. So what they proposed in this algorithm is that every node, right, for every node there should be two embeddings. Okay, one embedding is called the source embedding and the other is called the target embedding. Why? Say there is an edge from U to V. Okay, so with respect to this edge, U is acting as a source and V is acting as a target. Whereas if you have an edge from V to U, then V is acting as a source and U is acting as a target. Okay, so what they suggested is that every node is associated with two embeddings. One represents that node as a source node, other represents that node as a target node. Okay. So if you think of this case, as I mentioned, V4 is also close to V1, but V4's target embedding is should be close to V1's source embedding, whereas V4's source embedding should not be close to V1's target embedding, which basically indirectly says that there should be an edge from V1 to V4, but not V4 to V1. Okay. This is the embedding space. As you see here, these arrows are basically vectors, right. Again, dummy example, right. You see, so this is the notation that they are following. Let us say V1 is a node and U1S is a source embedding of node V1 and U1T is the target embedding of node V1. Okay. So you see here, let us say this edge, okay, this edge is U1S, meaning V1's source embedding, right. You see that this vector is closest to this vector, okay, and what is this vector? This vector is U2T and U3T, meaning 2 and 3 as the target nodes, right. Therefore, you see there is a directed edge from V1 to V3 and V1 to V2, right, and both their proximities are same. Therefore, U2T and U3T should be closest to U1S, right. And you also see that V3, so V3 and V2's source embedding, meaning U3S and U2S, okay, they should also be closest to V4, V4's target embedding, which is U4T, right. Similarly, V4's target embedding, right, you see here, this is V4, right, this is V4's target embedding, right. This is also closer to U1S, is also closer to U1S, okay. Right. If you note it here, another thing to note is very important. So look at here, say this is V6, okay, this is V5. You see that there are two directed paths from V1 to V4, right. But if you think of here, there is a path from V1 to V3 to V5, there is a path from V5, this is V6 to V5, right, but there is no path, there is no edge from V1 to V6, right. So V5 as a target is also close to V1, right, due to this path, but this is not as close as V4. Why? Because V4 is now connected to V1 through two paths, two shortest paths, right. So this is V5's target embedding. Okay. So if you look at V1's source embedding, this is V1's source embedding, okay, this one, and this is V5's target embedding, and this is V4's target embedding. So you see that this is closer than this one. So the bottom line story is that if there are lots of such shortest paths between two nodes, right, between U and V, although U and V are not directly connected, they should be closer. They should be close in the embedding space. Okay. So now this is the story. Now let us look at the formulation. So what they suggest is as follows. So they say that let's define a high order proximity matrix S. This is a high order proximity matrix. Now how do you calculate it? I am coming to that. Okay. So this high order proximity matrix can be calculated using, say, page rank. Now so each entry Sij indicates the proximity between Vi and Vj. Remember, this is not symmetric, right, meaning Vij should be not equal, Sij is not equals to Sji. Okay. So now this can be calculated in many ways. For example, this can be calculated using Cart's distance. We discussed what is Cart's centrality, the same as Cart's distance, right. We can also use page rank. We will discuss page rank types algorithm. We can also use common neighborhoods, say, for example, right, and so on and so forth. So they also defined two other matrices. One is called US and other is UT. So US is the n cross p matrix, whereas n is the number of rows, number of nodes, and p is the number of features, okay, embeddings. So US consists of all nodes acting as consist of all embeddings of nodes acting as source nodes, whereas UT consists of embeddings of all nodes acting as target nodes, same as this is also n cross p. Okay. So and S is n cross n, right, S is n cross n. So what is the idea? The idea is that you can factorize S into US and UT, okay, oppose transpose, right, and your target would be to factorize S, meaning to minimize the distance between two, right, in order to obtain the embeddings. This is the target. Okay. So then what they suggested is that every higher order matrix, every higher order proximity matrix S can be decomposed into what they call two polynomials of matrices. Okay. One is Mg inverse ML. Let's try to understand it. Let's focus on it. So let's say this S is a, as I mentioned, this is a proximity matrix, and let's assume that this is Cart's distance. Okay. What is Cart's distance? We have already discussed. S, say S Cart is beta, which is the decay parameter, the damping factor, right, a to the power L, where L equals to 1 to infinity. L is what? L is the distance. So, you are multiplying A with itself one time, two times. When you multiply A with itself A square, meaning you are looking at 2 hop, then 3 hop and 4 hop and so on, right, and you are looking at infinite distances. So, this can be decomposed into this can be written as beta A, and what is beta? Beta is decay factor. As you move along from 1 hop to 2 hop to 3 hops, L will regulate the decrease in importance. Okay. So, plus beta A, we can write it, right, recursive formulation. And so you have A scarced is beta A, right. You move this thing here, and then you calculate what you get. You get A scarced equal to I is the identity matrix, right, I minus beta A okay. As I mentioned earlier, every A's can be decomposed into this. You see here, this is your Mg and this is Ml. Okay. You see that when S is defined in terms of Cart's distance, you can easily get this kind of formulation. Let us see another such higher order proximity notation, formation, which is called rooted page rank. So, rooted page rank is same as random walk with restart types page rank. Okay. Essentially what it says is that this rooted page rank is the probability that a random walk from node Vi is located at Vj in the steady state. Okay. And how do you define this? S of page rank is alpha with alpha probability you basically move, right. So, since we are only calculating between I and j, so Sij PR, right, with transition probability P plus 1 minus alpha I. This takes care of the restart probability and this takes care of the jumping probability, right. What is P? P is the transition probability, transition matrix, stochastic matrix. Okay. Transition matrix such as this is stochastic. So, row, the sum of entries of each row should be 1, right. Say I j equals to 1 to n should be 1. Okay. So, this part if you write in terms of matrix, right, this would be you see here you can move this thing out here and then the remaining part will just be straightforward. So, sorry. So, this would be okay. So, here you see this is Mg and this is Ml. So, what they suggested is that they have actually looked at 4 such higher order proximity measurement formulation. One is scarced, other is rooted page rank, the other one. So, this is also rooted page rank is very same as random walk with restart, also same as personalized page rank, right, and so on. They have also looked at common neighborhood, right, and they have also shown that you can decompose into S into MGML, and they have also looked at atomic error distance. Okay. So, if this is true, then what is the actual formulation, right? Let us try to understand it now. So, now if this holds, that means, you can essentially solve this problem using SVD, right? You can decompose S, right? You can decompose S, right, with SVD, singular value decomposition. We discussed what is singular value decomposition in the last lecture briefly. So, it means that you will essentially have S equals to summation of, right, n number of nodes, this is your singular value, and then you have VIT transpose, right. This is singular value and these are singular vectors, right. But SVD is extremely time consuming. This is essentially order of n cube, right. Now think of large network, this is impossible to do, right. Therefore, they came up with a theorem, right, which basically says that you can just get rid of SVD part if you just calculate mg and ml, because all this all the proximity based formulations which essentially construct S, this can be decomposed into mg and ml. So, if you calculate mg and ml, which are easy to calculate compared to calculating S, right, the remaining part would be straightforward, right. And they also suggested some variations of SVD which they call as Jacobian-Davidson type algorithm for some sort of partial generalized SVD. I am not going into details of that, right. But it turned out that using this kind of approximations, you can easily ultimately your aim is to do get this one, right. When you get this one, then the remaining part is same, because this ultimately what is the final task? The final task is to get US and UT, these two matrices, right. So, then US would be this one and UT would be this one, okay. So, what they suggested, you first calculate mg and ml given a particular S, given a particular higher order proximity formula, you calculate mg and ml, and then you use this Jacobian-Davidson type algorithm, right, and then you obtain these singular values, right, and from singular values you can easily get US and UT, okay. So, this is the idea behind HOPE. In the next lecture, we will discuss another such algorithm which is called line, which is mostly useful for large network, which also kind of takes care of the higher order proximity, okay. Thank you.